What's the topic of today's lecture? The topic is memory, caches, and so on. I'm repeating this every lecture, that memory is the slowest part of your computer, and if you know how to optimize your software for memory, for accessing the memory, this is an easy way to get your software faster. So it's good that more people is coming. We can start. So this is the outline of today's lecture. First, we look at why memory is slow, whether we can do something with that, and we will see that there is not much what we can do except what is already being done, and that is use caches. And if we have caches, we need to know how caches work and how to use them efficiently, or how to tweak, modify our algorithms to use caches efficiently. So we will demonstrate some, I would say, simple algorithms for matrix multiplication, and on that I will hopefully show that working with caches efficiently can lead to very interesting performance boosts. And finally, we will talk about some other problems like false sharing and how to solve that, because this is a very tricky problem. If you don't know that this problem exists, you are very unlikely to figure out that it's actually a problem of your program, because it's very tricky. So we will look at that. So let's start by talking about why is memory slow. By talking about memory, I mean mainly DRAM memory. DRAM stands for dynamic RAM, and typically, or we distinguish like two most common types of memories used in the computers. The first one is static RAM, or shortened SRAM, and the other one is DRAM, dynamic RAM. So the basic difference between those two is that every bit in a static RAM is a circuit. Actually, this is a flip-flop circuit, which looks like this. And what you can see, that you need like 6 transistors to represent 1 bit. The advantage is that this is very fast. If you want to switch the memory from 0 to 1 or vice versa, it's very fast because it's flip-flop bit. It switches very quickly. But the disadvantage is the size of the cell and also power consumption, because all those transistors need to be powered, and when switching those transistors, they consume power. And because of that power consumption, they can switch fast, but if you switch too many of them too fast, the power consumption is pretty high. For that reason, there is also this other type of memory, dynamic RAM, where single bit looks like this, just a single transistor and a parasitic capacitance, and this capacitance just remembers this value. Either the capacitor is charged, meaning like logical 1, or it is discharged and it's like logical 0. So it's very the single bit is much smaller than in case of static RAM, but the disadvantage is that if you want to charge or discharge this single bit, you have to use like dynamical system, because you cannot charge it infinitely fast. It's like if you pour water into your glass, so you just pour the water and it takes some time until the glass fills. So this is similar with charging a memory cell like here. So it simply takes some time to charge it or discharge, to change the value from 0 to 1 and so on. So that's like the single bit thing. Of course, we are interested in having more than a single bit of memory, so we create chips of many of those single bit cells and connect it to the main CPU through a memory bus. So now we will look at the properties of this memory bus and properties of those chips which are composed of those single bits, because there you will also see the source of slowness, and you will, based on that, you will understand why memory behaves like it behaves and how to make it faster. So first, let's look into the DRAM chip, like the chips here. They can be, their internal structure of the DRAM chip can be depicted like what you see here. So it's an array, 2D array of those single bit cells. So this is 4 by 4, 16 bits memory. Of course, in practice, you have much bigger memories. And what you see here, you can imagine this is like a memory chip for a single bit memory. So the memory which is not composed of bytes or words, but from single bits. And if you want to read or write a single bit, you would use the data bus which is here. And to specify which bit you are interested in, you have to specify the address via those signals A0, 1, 2, and 3. This is just a 16-bit memory, so we just need 4 wires. But if we want to make it simpler, we could make like 1 bit for, or we could make like just 4 bits together to represent the whole address. But if we have like gigabytes or maybe even terabytes of memory, the outcome of this structure would be that we need a lot of wires here. So like 64 or 128 or even more. So for this reason, what hardware designers do, they decided to multiplex those address bits to actually 2 buses. And whenever you want to specify the address, or whenever the hardware wants to specify the address to the DRAM chip, it first sets like a row address, like those 2 bits, waits some time, and then it selects those the other part of the other half of the address via those address bits. So there is a sequence of operations. You first specify these bits, then you specify these bits, and then you can read or write the data. Because this is a sequence, this is not happening in parallel. This also slows things down. To give you a bit more details, this is the timing diagram of the communication protocol between the CPU, or specifically between the memory controller on the CPU and the DRAM chip. These are signals for individual wires. So there is a clock signal which just synchronizes the signals on the other wires. And then you have those address wires and data wires. And what you can see here the sequence. So first you specify the address of the row. So basically it means like those 2 bits. Then you wait a bit and you specify column address, so another half of the address. Then you again wait a bit, and then you can either read or write the data. So the question here is why you have to wait here and here. And the answer is that basically selecting this address here, for example, requires some changes, some communication inside the chip, and it's not like instantaneous operation. You just have to wait for the whole chip to propagate this change through all the wires and so on. And the key thing is that you cannot make this shorter. Of course, everybody tries to make this delay shorter as well as this delay, but due to like physics of the chips, it's not possible to make it shorter. So the outcome of all of this is whenever you want to read and write a single bit or byte or whatever small amount of memory, you just have to specify the address with lot of delays, and only after all this delay you can get the data. So that's the primary problem. And then if you have already waited this long for the first data, it would be very wasteful if you want to read another piece of data just to wait again for this amount of data. So this protocol does several things to make the memory faster. So once you wait this amount of data, you just don't read a single word of data, but the memory automatically sends, or you automatically write just a sequence of words from memory, which means that the memory is actually not random access memory. You specify the address here, but whenever you do specify the address, you just read a block of data, not just a single byte, not just a single word, but a full block of data to not to waste much time waiting for these delays here. The second optimization that happens in hardware is that, for example, if you are not changing the address completely, different row and different column, if you are changing, for example, only the column here, then you don't have to wait for another row. So you the hardware specifies just this column change, and you wait just this delay and don't have to wait for this green thing. Yeah, so these are the basics of the communication protocol between the CPU and RAM. If you are buying RAM to your computers, you know that you are typically buying depending on those parameters which just represent the delay in clocks. And you have different types of memory modules. Depending on you have DDR4, DDR5, and I don't know what else. The difference between those DDR4, 5 is basically how fast the internal clocking of the DRAM chip goes compared to this outside clock signals. And while it might look like that the higher frequency might actually help, here you can see that it doesn't help much, at least with the delays that we have here, because this is the list of some chips that were common a few years back. Nowadays you have something like DDR5, but like the numbers here would be quite similar. The clock frequency was, and even today is, like similar in the range of hundreds of megahertz. This frequency is multiplied depending on whether you use quad pumped or whatever, giving you different internal frequencies of the DRAM chips. And here, if you look at what would be the delay, so here this is the column address select latency. All those different chips, even the slow one, even the fast one, if you multiply this clock frequency by the parameters of this clock delay, which is like the parameter specified by the manufacturer, you will always end up with something like, in this case, 12 nanoseconds. So no matter how fast you buy this DRAM memory, those delays will be always the same, because this is like given by the physics of the chip. Of course, what gets a bit better are the frequencies of how fast the data can be delivered here once all those delays are over. So this is improved by higher frequencies, but those delays do not improve at all. And this is very important to understand why you want to when you want to optimize your memory performance. Specifically, and I will repeat it many times, basically what it means, whenever you access your memory randomly, jumping from one address to another, this gets very, very slow, because whenever you jump somewhere else, you have to change, in many cases, both row and column addresses, and you wait these green and red delays, which you cannot make shorter. So whenever you want to access your memory efficiently, you always want to do sequential memory access. And that's also what memory caches are designed for. So not only DRAM memory is designed for sequential access or optimized, but also caches. So let's look at computer caches. Let's look first what's the architecture of the caches, and then how we can use them efficiently. So I guess the basic principle of computer cache is more or less clear to everybody. So very briefly, so you have a CPU core, and whenever this CPU needs to access data or instructions from memory, it doesn't talk directly to this memory bus here, but there is a cache, typically on the same chip as the CPU. The CPU first asks the cache whether the data is in the cache, and if not, the cache then sends the request to main memory to read the data or to write the data there. In practice, the situation is not like this, or the actual architecture. We don't have just a single box, single component with caches. We have so-called multiple levels of caches. So all these caches are typically implemented as static RAM memory. And there are lower levels, like level 1, this is the lowest level cache. This is smallest but fastest. And then you have higher level of caches, which are a bit slower, but a bit larger. The first level is not only smallest and fastest, but usually it is also split into actually two caches, which are called level 1 instruction cache for fetching program instructions, for fetching the code, and level 1 data cache for reading and writing data. Because it turns out that if you split instruction and data caches, the performance is actually faster, because instructions in memory are accessed via different patterns than data in typical applications. So this is the cache architecture of a single core CPU, and that's not still how computers are designed today. Today we have multi-core CPUs, so this structure is actually replicated multiple times, and this is what you can see here in this picture. So there is one core with one local cache, in this case level 1 cache. There could be another core with its local level 1 cache, and then in the chip or in the socket, actually some levels of caches can be private to the core, and some levels of caches are shared among different cores. So typically it looks like that level 1 cache is private for each core, and level 2, level 3 or level 4, if you are some bigger CPU, those are shared to some extent, like through the whole chip. Typically the last level cache is shared like everywhere. And those middle caches, this may be varying. So this is the architecture, and now we will look at how to optimize your software for this memory architecture. But before we can do that, I have to talk a bit about terminology, which I will use later, or which is also common in the literature. So probably also a very well-known fact is that the basic principle why caches work and why they make your program run faster is so-called spatial and temporal locality. This is a property of typical computer programs, which means that if you access data in memory, it is often the case if you are accessing one data item, you will access data item next to it or close to it soon. So this is the spatial locality. Typically, whenever you have data structure, whenever you read a single field from the data structure, you will also read a next field or the other fields in the data structure. So this is the spatial locality property, and caches take advantage of this property by not loading a single byte of memory, but by always loading the whole chunk of memory, which is called cache line. So whenever you read anything within this cache line, next time when you read something else in the same cache line, it's already cached and you don't have to wait for that. The other property is called temporal locality, which means that in many cases, whenever you read some data in one part of the program, in another part of the program which gets executed soon, you read the same data again. So if the cache remembers the cache data for some time, it can help speed up subsequent accesses to the same data. So there are both examples for code and for data. So for code, most of the programs is composed of loops. So the CPU is reading instructions of the loop repeatedly over and over, and the same happens, for example, with data in this case. So these are the locality. Now the important terms are cache hit and cache miss. So whenever the CPU wants to read from memory, if the data is already cached in some cache, we call that cache hit. If the data is not in the cache and we have to go to the upper level memory or to DRAM memory, this is called cache miss. So we can say this is like cache hit or cache miss, or we can say this is level 1 hit or level 1 cache miss. If this is just level 1 cache miss, it can still be level 2 cache hit if the data is in level 2 cache and not in level 1 cache. So yeah, so talking about cache misses, this is like generic term, but the reason why memory access results in cache miss, there are multiple reasons. So we distinguish so-called cold miss, cache capacity miss, and so on. So cold miss, this is like obvious thing. Whenever you access the data for the very first time, it's clear that this data cannot be in the cache because it's the first time you are or the CPU is accessing them. So this is called cold miss because the cache is cold. Once we load the data into the cache, we say that the cache is hot, and we no longer have this cold cache miss. Another reason for cache miss is so-called capacity miss. Capacity miss means that you have already accessed the data in the past, but for some reason this data had to be removed from the cache because the capacity, the size of the cache is not big enough to hold that amount of data. So this is capacity miss. This is often like the biggest source of cache misses because the cache is just too small. Conflict miss, we will talk about that later, but conflict miss means that every location in the cache, it's called every cache line in the cache, cannot cache arbitrary part of memory. So only certain parts of memory can be cached in the single cell of the cache memory. And if this is the case, to cache something, we have to remove something which is already in that data in the cache, even though some other part of the cache is free, and this is called conflict miss. And then we have also true sharing and false sharing misses, and we will talk about that towards the end of the lecture, so I will just leave the discussion to that section. So The last bit of terminology is cache line eviction. So cache line eviction is a term which means that if a cache is full and I want to store some new data into the cache, to make some space there, I have to evict or remove some other data from the cache, and this is called cache eviction. And the cache eviction is driven by so-called cache replacement policy, which is an algorithm implemented in hardware, in the cache hardware. Typical examples of that algorithm is least recently used. This is like what everybody wants to have. We are just evicting the least recently used data, meaning the oldest data are removed. But for practical reasons, this policy is hard to implement in hardware quickly. So if you want to implement this in the hardware, it would be quite slow. So for that reason, different computer architectures implement typically either pseudo ALRU, which is like least recently used, but not in the whole cache, but only in a certain part of the cache, typically in one cache set. I will show you what that is later. Or in ARM CPUs often implement so-called random cache replacement policy. So which data gets evicted is determined by randomness. The advantage of that is that it's really fast. There is no need for synchronization between different parts of the caches, but it's random, so it's hard to do any predictable performance. You can do only some statistics, but for most of the needs, this is sufficient, especially for some consumer electronics, computers, and so on. So this is the terminology, and now let's look at different architectures of the cache. We will start talking about so-called direct mapped cache. This is like the simplest idea of the cache, but it's not used in practice because it has many disadvantages. Ideally, we would like to have what would be called fully associative cache. This would be nice, but it's hard to design it in hardware. There would be a lot of problems with that. So because of that, today's hardware typically implements what's called set associative cache, and we will look at all these into details. So let's start talking about direct mapped cache. So this is the simplest implementation of cache memory you can imagine. How does the cache memory look like? So the cache memory can be, you can imagine that like this. So these are some memory cells here. And these memory cells are somehow mapped to the cells in real memory. And this mapping is based on the address of the memory. So imagine this is a 32-bit computer. You can also imagine 64 bits, but then the number here would be 63. So if you have the address in memory, what you can do, you can split the address to different parts, like digits in a number. So lower digits represent offset within what's called cache line. So cache line is one part of the cache which is accessed like in one operation. Then the second set of digits in the address is the number of cache line, and then you have what's called tag. So how does it work? Whenever you are accessing some data in a memory, this middle part of the address just represents the cache line where this memory can be cached. So if you have cache with, I don't know how much is that, perhaps 8 cache lines, this direct mapping means that the first cache line can be used for caching the value in this piece of memory or this address at address 0, or here at address 512, let's say, and 1 kilobyte, and so on. So every 512 address, this will be mapped. That's why it's called directly mapped cache. This will be mapped to this line. So the cache knows that whenever there is something here, it's either the address 0, 512, and so on. And to actually know whether this address, for example, this one is cached in this cache line, the cache needs to remember the tag. So the tag is just the upper part of the address, and this is stored inside the cache so that the hardware knows whether basically we are caching here the green one or the red one or the yellow one. So this is how it works, this direct mapping, and you probably already see potential problems. But before we look at what potential problems are, I want to stress one thing. I often ask students what is at the exam, what is the size of the cache line, and often I hear the answer, I don't know. So please remember, typical size of the cache line is 64 or 128 bytes. In the past it was 32, nowadays like it's most common like 64. There are some newer CPUs, Apple M1, M2 probably too, they have like bigger cache lines, but it's bytes. It's not kilobytes, it's not megabytes, it's not bits. So it's 64 bytes. What does that mean? It means, for example, if you have an integer in memory, into this 64-byte cache line, you can fit like 16 32-bit integers. So it's not like big amount, but it's not even small. So it's 64 bytes. That's important. If you don't know what is the size of the cache line, it's very difficult to optimize for memory accesses. So 64 bytes. Why 64 bytes? In many cases, this is also the amount of data which you can read from DRAM in a single memory access. So here, this is the DRAM protocol, and whenever you do this is called DRAM transaction. So whenever you do this DRAM transaction, this data typically is the size of a single cache line. So whenever you are accessing the DRAM sends the whole cache line of data, and this whole cache line then gets remembered, gets stored in cache memory. So that's it. Now let's look at what are the problems with this direct mapped cache. So the typical or the most immediate problem is so-called self-evicting code. Question?
So the line size length, is it the same for every cache layer, like L1, L2, and so on?
In like most computer architectures that I am aware, yes. But I am not excluding that there might be some, let's say, obscure or experimental or whatever architectures where this is not the case. I'm not hardware designer. I believe that if the cache line size is the same, it simplifies the design. Yeah. But for example, this Apple M chips and also the GPUs, the size of the cache line can be switched between different sizes. So for example, many of GPU algorithms, especially the graphical ones, they configure the cache line size on the GPU depending on which algorithm is running there. So this is like heavily used to optimize all kinds of operations. And yeah, memory is slow, so there is a lot of tricky optimizations in memory subsystem and in caches, both from hardware and software sides. But we will do just simple things here. So we will just assume a cache line is 64 bytes, and all cache levels use the same size. So self-evicting code. So this is a problem. Imagine you have a program like this. There is some function. This function executes a for loop or whatever kind of loop, and in every iteration of this loop, it calls a function which is called inner function here. And you just write it into your program like this. Normally, you don't have control how this code is laid in memory. You just write it into the source code. And it can happen that the compiler and linker just lays out this code in memory this way. The outer function will be stored here, and the inner function will be stored here. And if you have direct mapped cache, it means that the code for outer functions and inner function just shares the same cache line. So what does that mean? The CPU executes this outer function, so the CPU reads from the code from this outer function, so the cache stores this blue thing here. Whenever you reach call to the inner function, the CPU needs to fetch the instruction of the inner function, so it has to evict this cache line from the cache, and it has to read this yellow cache line to the first cache line here. It executes this inner function, returns back to the outer function. It needs to fetch the instruction, for example, this I++, and jump back to the beginning of the for loop. But this is not cached, so it has to evict this yellow cache line and read again the blue one, and so on. So every iteration there are 2 cache line evictions, and every iteration something has to be read either from higher level cache or from the memory, which makes this loop quite slow. So this is definitely a thing that you don't want in your code. What can you do if this happens in your code? So I have already talked about that when talking about the linker. If you are programming in C, you can specify a function. This is like on Linux, on different compilers, this would be similar. You can specify its so-called hot attribute, and this is a signal for a linker that all functions which are marked as hot will be put close to each other. So if you would do this in this example, the result would probably be that the outer function would be here, inner function would be here in the blue area, meaning that both functions can be cached together in different cache lines, but they will be cached together, and there will be no cache evictions when you are jumping between outer and inner functions in every loop iteration. So this is the problem and how to solve it. I have said that we don't have directly mapped caches. Instead, we have so-called set associative caches, or we would like to have fully associated cache, meaning that every cache line here could cache whatever address, but this is difficult to implement in hardware. So instead, what we have is called set associative cache. Set associative cache looks like this. You don't have in the cache, you don't have just individual cache lines, but you have so-called cache sets, and each cache set is composed of multiple cache lines organized in ways. So this is a picture of so-called two-way set associative cache, because there are 2 ways. Typically, In today's hardware, you can find like 8-way set associative or 16-way set associative cache. There are like 8 or 16 those columns here. And what does that mean is that those addresses, which are multiples of the number of cache sets, can be mapped to the single set, but which of those addresses are mapped here, this can be determined freely as needed. So if you have this green, red and yellow memory parts here, the cache you can cache like 2 colors of those. Here I have just 3 colors, but if you have more memory, of course, you can have more colors here. But 2 of them, arbitrary 2 of them, can be cached in this cache set. So this is definitely better than directly mapped associative cache or directly mapped cache. If you want to understand the effect of performance, there were many studies assessing the performance, and basically the result was that if you have like 2-way set associative cache, it behaves similarly performance-wise, like if you have a direct mapped cache of the double size. So if you just organize the cache differently, like here we have, this is, I believe, 16 cache lines here. So this 2-way set associative cache would behave like a direct mapped cache of 32 cache lines. So instead of increasing the cache size, we can change the organization, and it has approximately the effect of that. So if you have 8-way set associative cache, it behaves like approximately 8 times bigger direct mapped cache. Of course, it's just some statistics, it's not like real, but the improvements on algorithms are in this range. Yeah, so in this set associative cache, now this cache replacement policy basically determines not which data is evicted anywhere from the cache, but this cache replacement policy just determines which cache line from each set gets evicted, because which set to use, this is hard-coded in hardware, but which way this needs to be determined, and here this is determined by this pseudo RRU or random or whatever cache replacement policy. So now the question is, we have seen this problem of self-evicting code. What do you think? Do those set associative caches help with this self-evicting code? Any idea? Yes. And do they solve that problem?
No, like they help to some extent.
Exactly. Yeah. So they help. So for example, if you have this 2-way set associative cache, it would mean that if you have this inner function here and outer function here, it would be okay, because both inner and outer function can be in the same way. But if you have like 2 levels of function calls, like outer function, inner function, and inner function, you would have the same problem. So it helps with the problem, but still this problem can occur, much less likely, but still can occur. So it's still useful to know about it, and if you detect the problem, you do something with that. So these were the architectures of the caches and problem of self-evicting code. Now, so far we have talked about reading the code, about reading instructions, but with reading data would be quite similar. Caches are also used for writing. Whenever you write something to memory, the data is stored just into the cache memory without going to the main memory. In most cases, this is what you want, because it's quite likely that you will need to access the same data soon. That's why it is the default. If you don't do anything with your software, this is just the default behavior, and this is called cache write back. So whenever you write data back to memory, it goes to the cache, and the data is stored in the cache, and the data goes to the main memory only later when this cache line needs to be evicted for whatever reason. In some cases, you know that you will never need to access the data again. If you know that, it is wasteful to just store this data in the cache, because in order to store the data, you need to evict some other data, and maybe you would need this other data later, but you would not be able to get them because these are already evicted. So if you know that you are writing some data that will never be needed again, or at least soon needed again, you can apply so-called write-through cache policy. This is like another mode of cache memory where the data is not remembered by the cache. The data goes directly to the main memory. And you, from software side, you can trigger this mode by special instructions, special hardware instructions. So you don't use just normal move or write, but you use special instructions. If you are doing that from C code, you can use the special header file provided by GCC compiler, but I believe it's all provided also by other compilers. And then there are instruction functions which are called _mm something. The names are a bit strange, but these are the names of the hardware instructions on Intel CPUs, which were first implemented to do this kind of thing. So you can either write a single integer to memory, or you can write like 128-bit word, and so on, different types. So these are special functions implemented by the compiler, which get translated to special instructions to not store data in the caches. So this is one technique of improving write or cache usage for writing of data if you don't need to store the written data in the cache. Another thing which is often used in many cases by graphics I would say not applications, but graphics libraries, is so-called write combining. Write combining is similar to write-through policy, but it means that you are not writing like the whole cache line, the whole size like here, but you are writing, for example, byte by byte, or typically, because this is graphics, you are writing pixel by pixel, but you know that you are writing like consecutive pixels in memory, basically filling all the full cache lines. If you use for this kind of algorithms, if you use this write through, it would mean that every single pixel would result in write to memory, which would be painfully slow. So for that, you can use this write combining, which uses special piece of hardware, which is write combining buffer or the store buffer, depends on the implementation, where those single pixel writes are written are written to this intermediate buffer, and only when this buffer is full, the full buffer is write through the cache to main memory, again leading to no cache line eviction and protecting data which are already in the cache. So this is how to optimize cache usage for writing. Now the question is why we should actually optimize it, and why we can optimize our programs for working with memory. To understand that, you need to understand like what I call here memory performance characteristics. And to see that, let's look at some benchmarks, some data where I have tried to measure like the performance of the memory. And what you see in this graph is how long does it take to access a single, in this case it's a single character, so we have an array of characters. And we have a loop, and in this loop we are just incrementing value of this single byte variable in this array, and we are doing that not just a single variable, but we are incrementing like the whole array. So for example, we can have like 64 kilobytes of characters, and we are repeatedly incrementing like all 64 kilobytes of characters, and then going back and just incrementing these 64 kilobytes. And then we can calculate from loop like this, we can calculate what is the average time needed to do this a single increment. And if we divide it by the CPU clock frequency, we can figure out how many CPU clocks it takes. Of course, it's in average, but we can figure it out. And what you can see, that depending on how big this array is, the operation is faster or slower. So if the memory is pretty small, it's like 1 or 2 clock cycles. If it is a bit bigger, it's more like 3 or 4 clock cycles here, and if it is even bigger, it's more like 6 or 7 clock cycles. So what does this mean? Why the performance is different? Of course, it is related to the size of the cache. If you look at parameters of the CPU where this was measured, you would figure out that the size of level 1 cache was 32 kilobytes. So whenever your data which you are working with and accessing it repeatedly in this for loop fits into level 1 cache, the memory access is pretty fast. Once the data no longer fit into level 1 cache, the data are stored in level 2 cache. Every access to this goes to level 2 cache, so it's a bit slower, and somewhere here might be some level 3 cache. You can see there is not big difference, but once you go out of level 3 cache, which is like, I don't know, 4 or 8 megabytes here, this gets again a bit slower. This is, I think, nothing critical. But the reason is that this is sequential access, and remember I told you sequential access is good. Computers are designed for sequential memory access. Now let's look how the same experiment would look like if we don't do sequential memory access, if we do random memory access, jumping at different addresses and doing the same. So the program looks almost as before. The only difference is that we are not using this index as the address, but instead we calculate the address like this. Do anybody here knows what is this? What is this formula here? So this is a so-called congruent pseudo-random number generator. So this is some way how to generate random numbers which is pretty fast. Typically, if you call a rand function or whatever, which is not like cryptographically secure random number generator, this is what the random number does. Basically, it do some addition, multiplication, and logical bit masking, and the sequence of numbers generated by this operation looks pretty random. So, for the purpose of this experiment, this is sufficiently random, and you cannot see that there is no hidden functionality by calling function like random or whatever. So this is just simple. What you can see, once your data fit into level 1 cache, it's fast. Then there are some jumps, and then it's pretty slow. So here we are in the range of like units of clock cycles. If our data is big, do not fit into the cache, it's like 200 times or 230 times slower than if the data is in the cache, which is significant. So now, what are these jumps? I have already said these are the different cache sizes. So we can also verify that this is the case. So in this experiment, what I have done, I used perf to measure how many. And in this case, this blue crosses here, or blue-green or whatever it is color, I measured the number of level 1 cache misses. So I used performance counters to measure number of level 1 cache misses. And once the number of cache misses was pretty low here, but once we ran out of this level 1 cache size, which was 32 kilobytes, we have seen there is a lot of level 1 cache misses. So clearly this jump here is caused by going out of the level 1 cache memory. Now we can do the same with level 2 cache misses. This is another color. You can see that level 2 cache misses are almost zero up until this point, and then it goes up. The reason why this is not so sharp, this jump here, is that level 2 cache is a bit bigger, and all interrupts and these other things which are running on the CPU also use some parts of the level 2 cache. So even here the jump is not so like steep. Now let's do the same for level 3 cache. Again, you can see level 3 cache, this is probably like 6 megabytes of level 3 cache, and then the cache misses go up. But you can see that here there is something going on, that not only this increase here is not caused only by level 3 cache, but there is also something else. This is not a very well-known fact. Usually people get used to think about level 3 cache, but there is one other important cache inside CPU, and this is called TLB cache. TLB is translation look aside buffer. This is a hardware cache responsible for translation of virtual addresses to physical addresses. So you know this virtual memory stuff. Every process runs in a virtual address space, and the memory management unit inside CPU needs to translate those virtual addresses to physical addresses so that it can go to the memory for accessing the data. The amount of TLBs is also limited, and typically TLBs are maybe I have a picture here. So this is how it looks like. This is the address. This is the address of memory, and different parts of the address are used for addressing page tables, page directories, directory pointers, and other things. And if the translation is not cached, the CPU needs to go through all those tables which are in memory and do this translation in a slow way. Once this translation is done, it gets cached, and next time you're accessing the data from the same page, this you can do it from the cache. But typically CPUs have less less TLBs than what fits into level 3 cache. So that's why this TLB misses start increasing even before level 3 misses start increasing, and there is some not significant but visible slowdown even here. So this is also a thing which can be improved if you see this in your program. And the way how you can improve it is to use so-called huge or super pages. You probably know, and if not, another important number to remember. Typical size of the page in computer system is 4 kilobytes. Modern new CPUs can have even like 16 kilobyte pages, but still majority and the default in many operating system is 4 kilobytes. But you can also select so-called hue pages, which on x86 architecture is like 2 megabytes. By default, the operating system tries to guess what would be the best, but sometimes or often, in many cases, it guesses it incorrectly. So your software can help the memory allocator of the operating system to decide whether you want to use huge pages or not. And if you are using huge pages in your program, it means that for addressing like 2 megabytes of memory, you need just 1 TLB. So if you have hardware with like this CPU 512 TLBs, if you are using 4 kilobyte pages, you can access just 2 megabytes of memory. If you use 2 megabyte pages, you can access 1 gigabyte of memory without TLB miss, which can also be some performance gain. Yeah, so this is this was related to TLB misses. You may want to optimize your program for that. Another thing which I mentioned just very briefly, another thing which is related to caches is called cache-related preemption delay. What does this mean is that if you execute your program, this program works with data, and this data is stored in local CPU's cache to some extent. If this program gets preempted, meaning the operating system decides to switch to some other programs, these other programs also need some data and evict some data from the cache, and after this program either finishes or the operating system decides to switch back to the original program, the original program continues, but let's say half of the data from the cache is no longer there because of the other program, and therefore it has to access the data from slower memory, and the program runs slower. So in many cases, one way of improving cache locality or cache hit ratio is to run your program non-preemptively. Of course, it sometimes collides with some other goals like latency and response time and these things, but depending on what you want, whether you prefer latency, low latency or high throughput, you can just disable preemption in your programs or in the operating system to improve the performance. So that was like generic introduction to how caches work, how we as a software designers or software developers can do something like improvements of by directly reusing the hardware features. Now we will look at other things, how we can improve some algorithms to work efficiently. In many cases, those algorithms are designed to work with some data structures. And so I will take it very briefly here. We can go like one data structure after another data structure, and I could tell you like how can be this data structure optimized for cache friendliness. You have cache optimized hash tables, cache optimized search trees, cache optimized I don't know whatever. typically you can always find some kind of library where people has already done that. So I will just mention very briefly that you always want to do as much memory accesses in a sequential way as possible. So for example, if you have arrays or vectors in programming languages, it is in many ways better than if you have dynamically allocated linked list. Because if you have a linked list where every node in the list is allocated separately, it's quite likely that if you are traversing the list, you are actually jumping memory here and there, which results in this random memory access pattern. And similar things, if you have a search tree, if you have, for example, binary search tree, every node is somewhere else in the memory, and searching in the binary search tree basically means random jumps in memory addresses. So for these cases, typical data structures like B trees or whatever is better than binary search trees where multiple data is located close to each other. Yeah. So that's what I have already said. These algorithms exist, but are typically more complex than what you can find in simple textbooks. Another important algorithm or another important data structure which you often use, and you may even not know that you are using this algorithm, is the algorithm used by memory allocator. The location of a memory that you allocate with malloc, new, or whatever your programming language uses is influenced by the memory allocator, and big portion of memory allocation algorithm is devoted to the fact that they want to allocate the memory close to each other so that there is higher chance that the memory is actually accessed sequentially and that there are no big jumps when you are traversing the data structures. So in the Java part of the lecture, you will hear about how Java virtual machine, which algorithms Java virtual machine uses, and you will see that there is lot of tricks to compact the memory, to allocate from a single area, and so on and so on. So the same can be applied in C languages as well. You can change your memory allocator if the default one doesn't work for the workload, and it's not like common for default for many like simple applications, but if you are doing something performance sensitive like graphics or some like optimization stuff, it's quite common to just use custom memory allocators. And now I want to give you an example of some still pretty simple algorithm where I can show how cache friendliness or cache optimization can actually improve performance of the algorithm. The algorithm is pretty well known. It's like matrix multiplication. You know it very well from, I guess, algebra classes. So if you have two matrices A and B and you just multiply them, you know that this can be calculated by the single element of the resulting matrix is calculated by summing rows and columns in the original matrices. And on the next slide, I will show you like the simplest algorithm, how you can implement it. If you implement it this way, it will be 10 times slower than the version of matrix multiplication optimized for caches. So you perhaps know the algorithm. The algorithm is written here. Basically, this is like 3 for loops, 3 nested for loops. The first for loop goes over the rows, the second one goes to columns, and so on and so on. I actually have this in animation, so I will just show you these animations, and on that we will see how and why the cache plays an important role in performance of this algorithm. So yeah, so you should see. Yeah, so this is the algorithm, or this is these are the matrices, and if I just track through the algorithm, you can see a red color. Red color is what is in the cache, and this is not like a real cache of the CPU, but this is like a simulated, very simple cache with LRU policy. So the darker the color is, the more recent value is there. And as you can see, if you are executing this this simple implementation of matrix multiplication, here for matrix A we are pretty happy, because as you can see, this black rectangle goes always over the red data, which is the data which is already in the cache. Here in the B matrix, you can see that the size of the cache is not big enough, and whenever we do a step of the algorithm, we always have to read data which is not cached, which is Y. So while for matrix A we have like almost 100% cache hit rate, here we have 0 cache hit rate, and it doesn't help at all to have the cache. So this is definitely something very wasteful. So the question is what we can do about that. I guess most of you can figure out that we can transform the matrix B, so that by doing this matrix multiplication we don't have to go column wise, but we can go traverse the memory row wise. And if we do this, situation is a bit better. Now we can at least reuse this spatial locality. Whenever we read data from this element, the whole cache line is read, which means that the next element here, the cache line is just two elements of this matrix for simplification. So here the next element is automatically read. So next time we do next step, this is cache hit. Now we still have cache miss, because the next next element is still wide, but still for matrix B we have approximately 50% cache hit rate. Here you can see the overall cache hit rate is like 70. It's get better. If I scroll it, it's like 80%. If the matrix B is not transposed, we can see like cache hit rate is like 63%. So this is definitely better. The performance is better, but it's still not like the best possible reuse of cache memory. What we can do, if we want to optimize the memory even more, we can implement the cache matrix multiplication in so-called tiled way. We split the matrix to so-called tiles, which is like a small submatrix, in such a way that the full tile fits into the cache. And if we do that, even this matrix B, we can get much more cache misses for matrix B. So by running the algorithm, it looks like this. There are like there are like different blocks. It looks like the algorithm is more complicated, but the cache hit rate is 89–90%, so it's even better. The algorithm is complicated. That's correct. You can see it here. Instead of just 3 for loops, this tiled implementation of cache matrix multiplication is actually 6 for loops. These inner for loops are just normal matrix multiplication as before, and those outer 3 for loops, this is like matrix multiplication for the tiles, like if a single tile is a single element. So this is it. Now it looks like this is already pretty good. You can see here that this already achieves like 17% of the original performance, so it's like 5 to 6 times faster than the original algorithm. But we can do even better. What we can do better is can be seen here. Let's see. We have this tiled implementation. But this time we will look not only into like last level cache hits and cache misses, but we will also look at first level cache hits and cache misses. So now with green color we see the content of level 1 cache, and with red color we see the content of level 2 cache. So imagine our level 1 cache is able to, the size of level 1 cache is just 2 cache lines. And as you can see, the number of level 1 hits is still not very good. Here we have approximately like 50% level 1 hits. Here, for example, and here we have again 80–90% of level 1 hits. So this is good, but here this is still not good. So what we can do, how we can improve that even more, is to implement so-called two-level tiled matrix multiplication. And it looks like this, that we perform the multiplication not only in blocks, not only for this level 2, but we will also do the same, even smaller blocks for level 1 cache. So the algorithm now looks like this. You can see that those green boxes are in this B matrix. Those green boxes are like read multiple times. And as you can see, here this level 1 hit ratio is, I don't know, like 70% or whatever. So it's definitely better than than before. So if you do this, you can have overall cache hit ratio like 87%, and out of that, or in total, 78% of cache hits are level 1 cache hits. Only 9% is level 2 cache hits, which are slower. So this is like this is typically what's used for like mathematical libraries. If you just use some mathematical libraries or NumPy or whatever and do matrix multiplication, this is what they implement there. And how does the algorithm looks like? So the algorithm, not sure whether you can read it, but instead of 6 for loops in a row, now this is 9 for loops in a nested for loops. But the principle is the same. Everything is just matrix multiplication for differently sized blocks, and they are nested to each other. So if you think about that, this is just for 2 levels of caches. Nowadays computers have like 3 or 4 levels of caches. So what you can actually do, you can implement this matrix multiplication recursively. For each level of caches you can implement, you can do this recursively, and then for the higher level of caches there will be recursion. So this is the formula which you can implement, and this is actually how this can be implemented. So if you are interested, you can watch those animation in full speed on this YouTube site, and you can, if you are interested, you can also play with the code. One interesting fact: I wrote these animations for this course like 7 years ago. And since that time it was on the internet, and last year, I don't know why, but last year it became viral on Twitter, so it is now very popular among the internet. Maybe you have seen it as well, so people can thank Open Informatics for that. Okay, so this is cache optimized algorithms for matrix multiplication. You can see that, or you could see that by optimizing the algorithms you can get pretty fast gain. So that's important. And another important is what we have done last week, the effect of caches for sharing of data structures between different CPUs on a multi-core system. Last week we have talked about caches and cache coherency protocol. You probably remember this picture, where I said that one of the problems is that if different CPU access the data from memory, the data are actually in caches. If multiple CPUs access the same data, the data has to travel from one cache to another, and this is slow. This is perhaps easy to understand, and what typically this is represented what's called by the algorithm which is called true sharing. So it's clear if you share some data between CPUs, this data has to travel between caches of different CPUs, and this is slow. So the typical example of true sharing is a code like this. So you have a counter. This is an atomic variable, and you have just 2 CPUs incrementing this counter. So it's clear that if you do this, the result is, if you do this on multiple CPUs, the result is something that like this picture. The cache line with this variable travels between one CPU and another, traversing through the whole system, and it's just slow. So yeah, so this is expected. You see this data is shared. There is a single counter which is shared between multiple CPUs. They are accessing that, so it's expected. The same situation happens if you have a mutex. Mutex is also a variable which is shared between multiple CPUs. If you access the mutex from multiple CPUs, its cache line where it is stored has to travel between different CPUs. If this is the case, there is a lot of performance, or this mutex becomes performance bottleneck. What you need to do, for example, you have to introduce more fine-grained locking, so you will not lock like the whole data structure, but for example different parts of this data structure. And if your algorithm allows that, if your algorithm allows that, different CPUs will access different part of this data structure and will not be actually shared. So this would be beneficial. Or you can use so-called per CPU data. So instead of sharing the full data structure among all CPUs, each CPU will have its own copy. like for example what we have seen or what you have seen with those statistics and per thread variables in this RCU homework. And only if you need some global data from all the threads, you somehow accumulate them together. So this is another way how to improve this true sharing. But if you do that, what can happen? What can happen is so-called false sharing problem. So you try to get rid of true sharing, and you may end up with false sharing. Or maybe you even not try to get rid of true sharing, maybe by mistake you design your application and you get the false sharing problem. This is a big problem because the fact that you have false sharing in your program cannot be easily seen from the source code, because it's really the side effect of how the code is laid out or the data is laid out in memory, and you don't see it. You just see that your program is slow and you don't know actually why. So let's look at an example of false sharing. So the same code as before. We have a counter, but now we don't want to have this contention, so we decide, okay, so let's have one counter for each CPU. Each CPU will just increment its own counter and there will be no sharing. The problem is that there is actually sharing, but it's not visible. From the program we see like, oh, there is per CPU counter, but in practice, often there will be sharing, because remember, caches work, or the granularity of computer caches is a single cache line. So what is shared is not a single variable, but is actually a cache line in the CPU. And if those two counters happen to be in a single cache line, and the probability of that is pretty high, because this is like 4 bytes and the cache line is 64 bytes, so the probability of those two variables are in the same cache line is high. If this is the case, then those CPU will still share the cache line even though they do not share the variable. So that's the problem. Detecting this problem is quite difficult, especially if you don't know that this problem can exist. There are some subcommands of perf tool, or some like profilers typically have some way of figuring out that whether there might be some false sharing problem or not. So first thing is that it's difficult to detect that it's actually false sharing problem. If you already know that this is a false sharing problem, then the solution is pretty straightforward. And the solution is to ensure that the per CPU data are actually aligned to the size of the cache line, so that two counters, two data structures which are supposed to be per CPU are guaranteed not to lay in the same cache line. So in a C or C++, in GCC or Clang compilers, this could be a way how you can solve the problem. You define the variable with this attribute align 64, assuming that 64 is the size of the cache line. And if you do this, each of those counters will be stored in different cache line, and this cache line will not be stored by the CPU. Of course, you should not hard code this 64 to your source code. You should like dynamically decide or dynamically specify the size of the cache line. There are multiple ways how you can do that. And compile your program specifically for the cache line of your hardware architecture. Yeah, so this is the false sharing. Now, to see some effect of false sharing, if you don't have the homework done from last week, you can easily implement false sharing there. So you have seen this, I have shown you replacing the random number generator with the classical rand function, but you can actually do something similar, not just replacing this rand r with rand function, but just removing this thread here, so that this seed is actually shared. And this is then more or less like the same effect as you are replacing this with like per CPU array like this. Here you have per CPU seed, but those per CPU seed are actually stored in the same cache line, and this is this would be the false sharing. And if you measure the performance, I have at least measured 40% lower performance than if you use like proper per CPU with per CPU variables without false sharing. So yeah, we should finish. So I will skip non-uniform memory access. If you are interested, just look at what it is and what you can do about it. I would just conclude that even today, if we count memories in terabytes, the size of data structures actually matters, because we have terabytes of memory in our computers, but this memory is slow. The memory which is fast is still pretty small, and if you optimize your data structures to use small data structure, this is the best way how you can increase the performance. So that's all from my side today. Thank you for your attention, and see you next week.